current and voltage drop in series and in parallel. Everything you need to know was in the thumbnail. If two circuit elements are in series, they have the same current. If two circuit elements are in parallel, they have the same voltage drop. There's nothing else to say, so let's keep going. You first see these rules when you're learning about resistors or capacitors. And the rules are exactly the same for both resistors or capacitors. But these are not the standard symbols for resistors or capacitors. They just look like generic cylinders. So why did I draw them that way? I did it to emphasize that these rules do not just apply to resistors or capacitors. They apply to many other things, including inductors, batteries, any other kind of voltage source, diodes, whatever you like. And here's a crucial detail. You can mix and match different kinds of circuit elements. And that's very important to remember. When you first learn this or this, you were probably just looking at combinations of resistors or combinations of capacitors, but in fact you can have a resistor and a capacitor, anything and anything, and the rules will still work. Now let's clarify exactly what we mean by series. These two are in series because this end here is connected to there, and there are no other wires, no other connections, no junctions of any kind. So any electrons that come out of there have to go straight into there because they have no place else to go. So if you know the number of electrons per second exiting this circuit element, you need exactly the same number of electrons per second entering over here, and that's exactly what current is, charge per second. If we did have a junction and another wire leading somewhere else, then these two would no longer be in series because the electrons, when they reach the junction, would have two possible routes to go. And if there's any current at all in this extra wire here, these two can't possibly be the same. What about the parallel case? Well, we see plenty of junctions, but junctions are beside the point in this case. What matters here is that this end of this element is attached directly to this end by means of a conductor, could be a copper wire or something else. And then the opposite ends are also connected up in the same sort of way. Whenever you have a conductor, there's essentially zero potential difference anywhere along that conductor, and so the potential right there is the same as right there. The potential right there is the same as right there, so the difference from there to there is the same as from there to there. Now, if you happen to have multiple elements that are exactly the same kind of element, you can think of them as one big element, which we typically call the equivalent element. So two or more resistors in series are equivalent to one big resistor. Two or more resistors in parallel are also equivalent to a resistor. And there are formulas for how to do this with resistors and how to do it with capacitors and various other things. I'm going to skip that, but I do have a few relevant links up there and in the description down below if you're interested. But now let's think about what happens when you convert from this to this. You know that the current coming in here has to be the same as the current through there, which is the same as the current through here. But this is equivalent to this, and this is equivalent to this. That current is the same as that current, and therefore the current through the equivalent circuit element is the same. What about voltage drop? There will be a certain voltage drop from there to there, which will be the same as from there to there. But of course, the voltage drop here added to the voltage drop here is the same as this voltage drop, which is the same as this. So you can see these look very similar, except there's an equal sign, there's a plus sign. We can play the same kind of game with elements in parallel. This is equivalent to that. That's equivalent to that. And we can see clearly that the potential difference from here to here is the same as from here to here, which is the same as from here to here, which is the same as that. What about current? The current you have coming in here is the same as there, but here the current splits. If you have a certain number of electrons per second coming in here, some of them will go through this, some of them will go through that. They'll pass through and then eventually join back together, so the current over here is the same as over here, which is the same as there and there. So if you've got 1,000,000 electrons per second coming in here, some of them go up here, some of them go down here. Maybe you've got 400,000 per second there, 600,000 per second there. They pass through, they join together, you're back to 1,000,000 per second. Once again, you can see that these are very similar. There's a plus sign, there's an equal sign. Now let's do a simple example. So here's a simple circuit. We have a voltage source here, also known as an electromotive force, or EMF. Here we have a resistor. Are these two in series, or are they in parallel? The answer is both. They're in series because this is connected right over to there. Whatever particles come out of here have no place to go but into there, and it's the same story across the bottom. They are in parallel because these two ends are connected together and these two ends are connected together. Thank you very much for watching. Please like and subscribe. If you're interested in being tutored online by me personally, I am available. There's some information in the description down below. And here's a link to my electric circuit playlist.